Good evening, everyone. Myself Sana Sheikh. I'm a second year PhD student at IIT Bombay. I'm taking live session of NPTEL course every week from 7 to 9 p.m. and the course name is Symmetry, Stereochemistry and Application, and the course instructor is Professor Anshuman Roy Chaudhary from ISR Mohali, and I'm the TA of this course. So today we are going to discuss the week 6 previous year assignment question, and we will solve those assignment questions as we are doing every week. So today's topic is the symmetry element. We have to find out the symmetry of the molecule and the optical activity for those molecules. And the second thing is we have to find out the IUPAC nomenclature. So because we have already discussed these two topics, so I will just give brief introduction about this topic and we will solve the questions here. So here you can see that a molecule is if a molecule is present, then we have to check the reflection symmetry, or we can say that the improper axis of symmetry is present or not. So first we will check the improper axis of rotation is there or not. If it is present, then the molecule will become achiral and it's optically inactive, and these molecules have a achiral point group. But if the it's absent reflection symmetry and improper axis of rotation is absent, then we will see that the molecule will be chiral and optically active, and these molecules can be a disymmetric or asymmetric depending on our point group. So these molecules have a chiral point group. So it's further divided into two groups. That's the asymmetric and disymmetric. If only C1 axis is present, then it is asymmetric, and if other point group is present like C and D and C1 etc., then the molecule will become disymmetric. So we have already discussed these things, so it was just a summary of the previous lecture. So now we can see here, if group of low symmetry is present, then the molecule will have C1, Cs or Ci point group. What is C1 and Cs and Ci? So here in C1 point group we have only C1 axis of rotation, that is identity, also it's called identity, and C1, that means the rotation by 360 degree. Rotation by 360 degree. So all the molecule which don't have any other symmetry element will always follow the C1 point group. Okay, this is called a chiral point group. Now the second one is Cs. Cs means only the plane of symmetry is present. Plane of symmetry means only sigma plane will be there in the molecule. No symmetry axis or improper axis of rotation will be there, so it's called a Cs point group. Now what is Ci point group? In Ci point group we will observe that the center of inversion only. So this is the Ci group. So now let's talk about the group of high symmetry. So in group of high symmetry, we will observe that the tetrahedral, octahedral, icosahedral, C infinity V, D infinity H. So in tetrahedral molecule, all the bond angle, bond length will be same. Bond angle and bond length should be same. So that's why the molecule which have all the four ligands same, all the ligands are same, are come under tetrahedral. And similarly in case of octahedral and icosahedral, in if all the ligands and bond angle, bond strength and bond length will be same, then a molecule will be symmetric and it will come under octahedral and icosahedral. Now let's talk about C infinity V and D infinity H. So then here we will take the example of C infinity V. So I am here taking diatomic molecule, heterodiatomic molecule HCl. So in case of HCl, you can see that if I will pass the axis of rotation from here, So if I will rotate by 1 degree, and we can rotate till 360 degree, you can check from 1 to 360 at any angle. If you will rotate the molecule, you will get the indistinguishable image of the molecule. That means here we have infinity order of axis. Infinity order of axis means you can rotate at any angle. So that's why we can call it C infinity is present. Order of symmetry, order of rotation is infinity. So C infinity is present. Now let's talk about the subsidiary axis or other axis of symmetry, which is perpendicular to the principal axis. So can you see here any other symmetry axis? No, if you will see here, because it's a diatomic heterocyclic, sorry, heteroatom are present and it's diatomic molecule. So you will see that here we have H and here Cl, so both are different. So we don't have C two axis of rotation or any other subsidiary axis of rotation, so it's absent here. So we can call that only we have C infinity. Now let's talk about the plane of symmetry. So as you can see here, horizontal plane is also absent. So now we can check the vertical plane. So here we have infinite vertical plane. Infinite vertical plane is present, so we can write here C infinity V. So this is the point group we have here, C infinity V. Now let's see here, in case of the D infinity H, I am taking here example of acetylene. All of you know acetylene. Here I am writing acetylene. So here we have acetylene. We will check here other symmetry element which is present in this molecule. So if we will see that here we have principal axis of rotation or axis of rotation here C infinity, again C infinity, because it's the vertical axis. And now we will check the perpendicular axis. So here we can see that perpendicular axis is present, which is subsidiary axis C2, because the if we will cut the molecule from here, we can see that the upper half is same as a below half. So that's why we can say here we have C2 axis. Now we can see here we have horizontal plane also, because the molecule is symmetric from this center. We can say here we have center of inversion also. Center of inversion is also present here. So here we have horizontal plane. Now we will check the vertical plane. So here we have infinite vertical plane as a previous example, same as a previous example. So that's why we can write here, because we have both the axis, subsidiary and principal axis. That's why we will write here D for both the axes. And the highest fold of symmetry of the axis is infinity. Highest fold of rotation is infinity. Now because we have horizontal plane, I will write here H. So the point group will become D infinity H. So these are the highest symmetry point groups. So now let's talk about the other point groups. So highest order rotational axis is present if in a molecule is present, then we will check for the perpendicular C2 axis, that is called as subsidiary axis. If it is present, then we are writing D, as I have written here D. If it is absent, then we are writing C, as we have checked in C infinity V, right? Now if after writing D, we will check the plane of symmetry. If sigma H plane is present, then we will write D and H, what we have written here, D infinity H. N is the highest fold of rotation. Now if it's absent, we will check the dihedral plane. If dihedral plane is present, then we will write D and D, and if it's absent, then we will write only D and. Okay. Now let's talk about the other case. If perpendicular axes are absent, then we are writing C, as we have written here. And if sigma H is present, we will check the horizontal plane. If it's present, we will write C and H, and if it's absent, we will write the C and V. Sorry, we will check the vertical plane. If vertical plane is present, then we will write C and V, and if vertical plane is also absent, then we will check for the improper axis of rotation. And if improper axis of rotation is absent, then we will write CN directly, and if it's present, we will write S2N. So I hope these basic things are clear to you. Now we will start the question answer solution. So this is the first example. So here you can see that if I will pass the axis from here, axis of rotation, I will check here. So I will not get the exact molecule which we have earlier. So I will draw here after rotation. If I will rotate by 180 degree, what will happen? These two Cl will go below side, and these two hydrogen will come top side. So now these two structures are not same, not indistinguishable. So the axis of rotation is absent here. Axis of rotation is absent here. Now let's check the other axis here, or this way. So it's also absent. You can cross check by yourself. So all the axis of rotation are absent here. Now we will check the plane of symmetry is present or not. So here you can see that if I will pass plane through here, so we can see that these two are a mirror image of each other. These two halves are mirror image of each other. That means the plane of symmetry is present. That means sigma plane is present. So here we can see that other than sigma plane, no any other symmetry element is present. That means the molecule have only sigma plane. So the molecule with only sigma plane are comes under C as point group. Comes under C as point group. So this molecule have C as point group, and the because we have plane of symmetry is present here, so the molecule will become symmetric. The molecule will become symmetric, and because symmetric molecule are always achiral, so the molecule will become achiral. And the relation between chirality and optical activity is that if the molecule is achiral, that means it is optically inactive. Optically inactive. The molecule is optically inactive. Correct? So this is the relation. The point group of this molecule is CS, and it's symmetric, achiral, and optically inactive. Now let's talk about the other one. So here we will check the axis of rotation and plane of symmetry. So first I am checking the axis of rotation. So after, if I will rotate by 180 degree, this molecule by 180 degree, what will happen? What will happen here? This is again the same example, but only the difference is here. Previous one was cis and this one is trans. So the previous one was cis dichlorocyclobutane, and this is the trans dichlorobutane. So here what will happen after rotation? We will get the Cl here, hydrogen here, and Cl here, hydrogen here. This Cl will go here, and this Cl will come this side. Correct? So because now you can see that both the image have same, both the images are same. The only difference is position of Cl, and that means it is indistinguishable from the original one. So we can say here improper, sorry, we can say that rotational axis of symmetry is present here. So here we can say because the C2 axis is present here now. Now let's talk about the plane of symmetry. We will pass the plane through here and we'll check the symmetry is there or not. So we can see that both the halves are different. They are not mirror image of each other. That means the plane of symmetry is absent here. Plane of symmetry is absent here. So we can check the other symmetry element also, which is not present here. Center of inversion is also absent and other axis also. So that means we have only C2 or rotational axis of symmetry. So that's why, because the point group we have here only the symmetry axis is present. So I will write here C2. C2 point group will be the point group for this molecule, and because we have C2 point group, it comes under CN group, which we have discussed here, right? This CN, and because this CN is comes under which molecule? Chiral and disymmetric, correct? So the molecule will become disymmetric. It is a disymmetric molecule because C2 axis is present, axis of rotation is present, that's why. And because the plane of symmetry is absent, that's why the molecule will become chiral. The molecule will become chiral, and it's active optically active, correct? So now next example. So here you can see that in this example we have the same molecule, but the only difference is that we have bromo substituent instead of chloro. So this is a cis chloro bromo cyclobutane. So here you can see that you cannot pass the axis of rotation here because both the chlorine and bromine different halogens are present. So if you will rotate by 180 degree, you will not get the exact image which is we are observing from identical molecule. So it's not present. Now you can pass the plane of symmetry also, which is also not present. So both the C2 absent, sigma plane is also absent. Now the if molecule don't have any other symmetry element, then the molecule comes under C1 point group, as I have discussed earlier. Here you can see that here we have C1, right? If the molecule have C1 symmetry, then that means the molecule is chiral point group, and it comes under asymmetry. It's a asymmetry. No other CN is present, correct? So this molecule is comes under C1 point group, and because C1 point group is a chiral point group, it's a asymmetric molecule, and it is chiral. It is chiral molecule, and because it's chiral molecule, it is optically active. Optically active. So I hope all of you are clear here. It's a optically active molecule. Now let's talk about the other one. So here we have trans chlorobromocyclobutane. So in trans chlorobromocyclobutane, again you can check the axis of rotation and plane of symmetry. And if you will apply these two symmetry element, if these two symmetry element is present, then we can say that, sorry, yeah, you can check here these two symmetry elements are absent. So we don't have C2 symmetry and we don't have sigma plane also. You can pass the plane here and check by yourself. You can pass plane through here also, any plane. Now you will observe that there is no plane of symmetry is present in this molecule. That means sigma plane is absent. Again, because all the symmetry elements are absent, that means it will comes under C1 point group, which is chiral point group. C1 means rotation by 360 degree. If you will rotate the molecule by 360 degree, you will get the exact molecule as you have earlier. So because it comes under C1 point group, that means it is asymmetric. Again, it is a asymmetric molecule, correct? Asymmetric and chiral and active optically active molecule, correct? I hope all of you are clear here also. The second example is 1,3 cis 1,3 dichlorocyclobutane. You can see that if I will give the numbering through here 1 2 3 4. So the substituent are present at 1 third position. That's why 1,3 dichlorocyclobutane, and because both the chlorine group are upside, that's why we will write here cis. So we will check here symmetry elements present or not here, which symmetry element is present. So let's talk about this element. The first we are checking always its axis of rotation. So if I will pass the axis of rotation through here, what will happen? The molecule will rotate completely by 180 degree, and both the Cl group will go downside. That means it is not present. It is not present because both the Cl group will go downside, and it will not remain the molecule which we have as a initial stage. The molecule will become changed because in original molecule we have both the chlorine atom at upside, but if we will rotate by 180 degree, it will go downside. So that means it is not present. Now let's talk about the other symmetry element. Other axis. Any other axis is possible? No. Correct? No other axis of symmetry is possible here. You can check by yourself. Yeah, one possibility is there. Anyone? You can pass the axis through here from the center, right? And if you will rotate by 180 degree, this molecule by 180 degree, what will happen? This chlorine group will go this side and this will go this side, correct? This way. If rotation will take place this way, you will get the indistinguishable image of the original molecule. That means here we have C2 axis present. C2 axis is present, correct? Now we will check here plane of symmetry is present or not. So here I will check the plane of symmetry. Now because we have C2 axis, we will pass the plane through here, correct? I'm passing the plane through here. Now you can see that this half is same as a similar to the other half. The two halves are mirror image of each other. That means sigma b plane is present. Why sigma b? Because it's parallel to the axis of rotation. So if any plane is parallel to the principal axis, we are always writing v. It's a sigma v. Correct. Now any other plane of symmetry is present? Anyone? Can you pass the horizontal plane? No, if I will cut the molecule this way, because both R and Cl are different atoms, heteroatoms, so it's not interchangeable. So we will not get the same other half. That means it is not present. Correct? So here we have only sigma V and C2 symmetry. So the point group of this molecule will become C2V. Correct? C2V. You should check all these example by yourself, and we can discuss any difficulty doubts in next lecture. So please try yourself. So the point group of this molecule is C2V, correct? So because the plane of symmetry is present, that's why the molecule will become the molecule will become symmetric because of plane of symmetry, correct? And symmetric molecule always have a chiral point group. A chiral point group. So this point group is a chiral point group, correct? A chiral point group, and the molecule will become a chiral. And because the chirality and optical activity relation, according to chirality and optical activity relation, a chiral molecules are always optically inactive. So this molecule is optically inactive. Optically inactive. Okay. I hope all of you are clear here also. So we will move to the next example. Now this is the same example as the previous one, but the only difference is that here we have trans. trans 1,3-dichlorocyclobutane. Try to give name also. IUPAC naming is also important for you. So always try to give a name for a particular molecule. So this one is trans 1,3-dichlorocyclobutane. Correct? Now in this molecule, we will check the symmetry element present or not. So here you can pass the axis and you can check it is present or not. So if I will pass the axis through here, yeah. So in previous case, what we have done, we have passed the axis through this point, correct, in this way. So in this case it is not possible because both the chlorine have different phase, its upside and its downside. So this axis of rotation is not possible, so we will check for the other axis of rotation. So other axis of rotation is present or not? So it is there. So if I will pass the plane through, pass the axis through here by intersecting these two carbon atoms. In previous case, we were not passing the axis through any carbon atom. It was passing through the center. But here we are passing these through these two carbon atoms, and we will rotate it by 180 degree. We will rotate the axis by 180 degree. So what will happen here? This chlorine will go this side and this chlorine will go this side, correct? So that's why we can call here C2 axis of rotation is present. C2 axis of rotation is present. Any other axis of rotation is there? Yeah, you can see here we have this axis of rotation also. Sorry, here if I will pass the axis of rotation through this point by 180 degree, what will happen? This chlorine group will go downside and this chlorine will go upside. That means we have here other subsidiary axis, or we can say other rotation axis C2. There are two C2s. Now we will check the plane of symmetry is present and or not. So here you can see that you can cut the molecule by this way and you will get the two equal halves, two equal halves of the molecule, right? Now you can cut the molecule through this way also, and you will get the, you will not get the other half because here we have hydrogen, we have chlorine, so we have only one plane, this one. So because of that plane we have only one plane of symmetry, which one? Through here, sorry, through here, right? If I will cut the molecules, this half is similar to this half, so we have 2C2 and sigma plane. So here we one C axis of rotation, here we have one axis of rotation. So because this is perpendicular to the principal axis, we can call perpendicular axis. So that's why the point group of this particular molecule will become C2H, because horizontal plane is present, perpendicular plane is present, correct? So it will become, sorry, because we have subsidiary axis also, so it will become D2H. Sorry, because we have both the axis, principal as well as subsidiary axis. Here we have discussed, I will show here. Yeah, here you can see perpendicular axis C2 axis is present, highest rotation axis is C2 only, so we have D group. So here we have D group, so D2H, because horizontal plane is present, so the point group of the molecule will become D2H, which is a chiral point group. And because a chiral point group are and plane of symmetry is present, the molecule will become symmetric, achiral and optically inactive. Symmetric, achiral, and inactive optically inactive molecule, correct? Okay, now check the other example. please cross check these examples by yourself. Maybe I missed some symmetry element or some other things, so we can discuss simultaneously with our next class. So please try by yourself. So here the next example is here. So this is the 1,2 dimethyl cyclohexane, cis 1,2 dimethyl cyclohexane, because both the CH3 group are front side. So because this is cis 1,2 dichloro, cis 1,2 dimethyl cyclohexane, so we'll find out the symmetry here. If I will pass the axis of rotation here, what will happen? Both the CH3 group will go backside. Correct? Both the CH3 group will go backside. So here we have on front side. So this is not possible for this molecule because we will not get the indistinguishable image of the molecule. That means the axis of rotation is absent. C2 is absent here. You can pass by other carbon also and you can cross check by yourself. It's absent. So C2 axis is absent. Now let's talk about the plane of symmetry. So can I pass the plane through here? Yeah. If I will pass the plane through here, what will I will get? I will get the exact other half or mirror image of the molecule. That half molecule. That means we have a plane of symmetry is present here. Plane of symmetry is present here. Correct? Plane of symmetry is present here. Let's check about the any other point group. Is it possible to have any other symmetry element here? No. No other symmetry element is present in this molecule, so the molecule will comes under CES point group. We have discussed the first example, very first example. So this is the CES point group, and because the plane of symmetry is present, the molecule will become symmetric because it comes under chiral a chiral point group, a chiral point group. So the point group of molecule is CH, symmetric, achiral, and what? Optically inactive. Optically inactive. Now let's check the other example. This is the 1,2 dimethyl cyclohexane, trans 1,2 dimethyl cyclohexane. So this is a trans example, same as we have done in case of cyclobutane. We will pass the axis which is here through these two carbon carbon bonds. So here you can see if I will rotate by 180 degree, what will happen? This methyl group will go here downside and this methyl group will come first side. I will draw here. Correct? CH3. So it will go downside, it will come front side. Correct? That means we have C2 axis present in this molecule. Now let's talk about the plane of symmetry. So if I will pass the plane through here, what will happen? We will not get the exact half because it's the back side one and this is the front side. So this is not the mirror image of the molecule. So that means the plane of symmetry is absent. So the only thing is present in this molecule is rotational axis, that is C2 axis. So the point group of the following molecule will become C2, and because C2 comes under a chiral point group, so because yeah, so because chiral point group have optical activity, and we will write here chiral molecule is chiral and optically active, and because it has C2 symmetry, so because of C2 symmetric it will comes under disymmetry, optically active, optically active, disymmetric, disymmetric. Correct? So this is a correct example. This is optically active. Now this was the example of chirality of the molecule and optical activity. So now we will talk about the IUPAC nomenclature we have discussed in a previous class. So based on those topic only, those concept only, we will solve these two examples. So here we have two example of IUPAC nomenclature. So the first thing in any IUPAC nomenclature, what we have to do, we have to find out the three things: prefix. I have already discussed these things, correct? Prefix, parent chain, and suffix, correct? And suffix. Suffix. So, what is prefix, parent chain, and suffix? So, prefix is nothing but the substituent present on parent chain. Substituent present on parent chain. Now, let's talk about the parent chain. Parent chain is nothing but the longest linear carbon chain of any molecule. Longest linear carbon chain of any molecule, and suffix is highest priority functional group present in a molecule. So let's talk about this molecule. So here we have to find out first suffix, because if we will find out the suffix, then we will not include the suffix in a prefix, because it's also a substituent but the priority is highest, that's called a suffix. So here we have how many substituents: methyl, methyl, ethyl, and hydroxy. So first we will find out the parent chain, then it will become easy to find out here. Here I am selecting this chain as a parent chain, that means a longest linear carbon chain. You can see here all the atoms are present in this molecule is carbon, in this chain is carbon. So now how many carbon atoms are there? 1, 2, 3, 1, 2, 3, 4, 5 and 6, because it's a ethyl group. 6 carbon is also present. Now we will find out the suffix. What is the suffix here? This hydroxy group is present as a substituent, and these two methyl group are also present as a substituent. But the priority order is highest for hydroxy because it's the oxygen containing functional group. So the highest priority functional group of this molecule is hydroxy group. So we will not consider this hydroxy group as a substituent. Okay, as a prefix we will not consider this one. So because we have 6 carbon atoms, so we have to write here hex. Hex for 6 carbon atom, correct? Hex. Now let's talk about the substituent present on the molecule. So first we are writing prefix, that's why I have written dash here. So we have two substituent present on the molecule, both are methyl group. So what's the position of these two methyl group? 3, 4. So I will write here 3, 4 dimethyl, because two methyl group are there. So 3, 4 dimethyl. What? Dimethyl. Correct? 3, 4 dimethyl. Now we will write here parent chain name, right? Parent chain name. So here we have parent chain name hex, because 6 carbon atom is present. Now is there any other any double bond or triple bond is present in a longest linear chain or not? We have to check that one. So here you can see that we have a double bond present in a longest linear carbon chain, and it's present at third position. So and it's a alkene class, double bond is from alkene class, that's why we will write here 3 ene, because we have double bond present, ene, 3 ene, correct? Now in last what we are writing? We are writing suffix. So what's the suffix here? Alcohol group, and it's present at second carbon atom. So that's why we will write here it's present at second carbon atom. So we will write here 2-ol. Ol for alcohol, 2-ol. So now this is the name of the molecule 3,4-dimethyl hexene 2-ol. Because we have here chiral center, you can see here we have chiral center. So we have to find out the RS nomenclature as well and EZ nomenclature also, because we have here alkene group. So RS and EZ nomenclature we will find out here. So I will write here first EZ nomenclature. So here we have ethyl group, it will have first priority, then methyl group will have second priority, then here this group will have first priority and this will have second priority. So because both the second priority group are on same side and one is same side, that means it is a Z alkene. Z alkene. So I will write here Z alkene. Now we have to find out the RS nomenclature. So in RS nomenclature we are giving the priority numbering. So here first priority will be given to the hydroxy group 1 and the second priority will be given to this whole chain, carbon atom, whole group. And because this is the only chiral carbon atom present in this molecule, that's why we are finding the RS nomenclature only for this carbon atom. So this second will be given to the whole chain and the third will numbering will be given to this carbon methyl group and fourth will be given to the this hydrogen group. Correct? Now what's the rotation here? 1 2 3. So this is anti-clockwise or counterclockwise. So S group is present. So the S absolute configuration will be given to the molecule. So then IUPAC nomenclature, according to IUPAC nomenclature, the molecule's name will become SZ34 dimethyl hex 3-ene-2-ol. All of you are clear here? Please try to solve by yourself. Then we can discuss more examples. Please. Okay. Now this is the last question. So write the IUPAC name of the following molecule. So in this molecule you can see that how many carbon atoms are present. First I will write prefix, parent and suffix. Then we will go sequentially order by order. Your parent. And the last one is suffix. Correct? So here what is the parent chain? I will take this chain as a parent chain. You can try by yourself also by taking this ethyl group in a chain and by including this chiral group also. But because according to IUPAC rule, we should include the chiral carbon also because we are giving the numbering and label to that carbon atom also. That's why it will better to include this carbon atom. Now we have to include the double bond also in a longest linear chain. So here I have included those things. Okay, so this is the longest linear carbon chain. We will give numbering 1, 2, 3, 4. I am giving numbering from this side because we have to first see the highest priority functional group present in the molecule as a suffix. So here also we can see we have chloro and hydroxy group. So hydroxy have highest priority functional group. Hydroxy group have a highest priority. So that's why this is used as a suffix and we have to see that in the longest linear chain we have to observe that the highest priority functional group will be always present on a lowest number carbon atom. So from this side we will get only 2 number here. From this side we will get 1 2 3 4 carbon number. So that's not the correct one. So from this side we will take carbon number 2 here. So this is the uh, longest linear chain. Yeah. And how many prefix are present on the this longest linear chain we will see here. So we have one chloro group and one ethyl group. Correct? So what I will write here, because we have to go alphabetically for substituent present on the parent chain. So at carbon number 2 we have chloro group and at carbon number 3 we have ethyl group. So at alphabetically chloro group will come first. So I will write here 2 chloro, 2 chloro, 3 ethyl. Ethyl group is present at carbon number 3. 3 ethyl. Now parent chain name. What's the parent chain name? Here we have 5 carbon atoms. 5, so it comes under pent. Correct? It will come under pent. And because we have double bond present in longest linear chain, so we will write the position of double bond and the class of that group. So here we are writing 3 and because it's alkene class, so we are writing here ene. 3 ene. Now at carbon number 2 we have alcohol group, so we will write here 2-ol, 2 alcohol, correct? So this is the basic name of this molecule. Now we have to find the Ez and Rs nomenclature. So first we will find out the Ez. So what's the Ez nomenclature here? In methyl and hydrogen, first priority will be given to methyl group, second is hydrogen, correct? In here, in this case, first priority will be given to this whole group and the second will be given to the ethyl group. Now you can see here we have second and one at same side and two and one on same side. That means it is a E group. E is E alkene, correct? It's a E alkene. Now let's talk about the chiral carbon present in this molecule. So you can see here we have only one chiral center here, only one chiral carbon atom, and we have to find out the absolute configuration of this carbon atom. So for the absolute configuration, what we are doing, we have to give the priority to the group present on the particular group. So here we can see that the first priority will be given to the hydroxy group. It's the highest priority functional group present in the molecule, and the second priority will be given to this chlorine atom, and the third priority will be given to the whole group present here, and the fourth one will be given to this methyl group. So if I will rotate the, I will observe the rotation here, 1, 2, 3. It's going clockwise direction, that means R, correct? It's going clockwise direction. But according to the absolute configuration and nomenclature, as RS nomenclature rule, if the lowest priority functional group is present on front side or a wedge position, we have to change the absolute configuration of the molecule. So here the lowest priority functional group is methyl group, and it's coming towards ourselves. That means it's present on front side, correct? It's present on front side. So that's why we will change the absolute configuration and it will become R, oh sorry, S, because R we are getting after rotation. So the correct name of this molecule will become Se2-chloro 3-ethyl pen 3 in 2-ol. Okay, this is the correct nomenclature IUPAC name of this molecule. So I hope all of you are clear till here. So I will just give a brief summary of the today's lecture, and that's all for today's lecture. We will discuss the doubts. In today's live session, what we have done, we have done the summary of the point group of the molecule. So if a molecule have symmetry axis as an axis, then it will come under a chiral molecule and optically inactive, and if it's absent then it will come under chiral and disymmetric molecule, correct? And chiral molecule also have two different types, C1 and C and DN point group. In C1 the molecule is asymmetric, and in case of this point group the molecule will be disymmetric. So these we have discussed the point group, how we can assign the point group. So just cross check by yourself and try to solve by yourself. If you are not getting an answer, you can discuss me in a next lecture. Now this is the first example we have done. Here all the symmetry element was absent, only the sigma plane was present. So because of the sigma plane, the symmetry was present in a molecule, and molecule was become symmetric and achiral, because symmetric molecule was achiral and it was optically inactive, correct? This is a trans example of the previous question, and in this case we observe that only C2 axis of rotation was present and no other symmetry element was present. So all the symmetry element was absent. That's why the molecule was become disymmetric, because of C2 point group, and it was chiral and optically active. Okay. So we have done the third example, in which we have the two chiral center and all the different substituent was present on those carbons. So because of the different halogen present on those both the carbon atom, we didn't observe any symmetry element in this molecule. So the only symmetry, lowest symmetry was present was C1 and E, and because of this lowest symmetry, it comes under chiral point group, which is C1. C1 chiral bond group, and the molecule was asymmetric, chiral and optically active. Then we have done the other example with trans chlorobromocyclobutane. So in trans chlorobromocyclobutane, again we observe that there was no symmetry element was present except the E and C1. So because of the lowest symmetry, it will comes under again C1 point group, and it will show the chiral point group and optical activity. So it's optically active and asymmetric molecule. So we have done the other example with 1,3-dichlorocyclobutane. In previous case we were observing the substituent present at 1,2 position, but in this case we have 1,3 substituted cyclobutane. So because of this one, we observe that the here C2 axis of rotation was present along with the vertical plane of symmetry. So because of vertical plane of symmetry present in this molecule, we got the point group C2V, and because the plane of symmetry was present, the molecule was become symmetric, and because of symmetry, the molecule is a chiral and optical, shows the optical inactivity. So the molecule was optically inactive. So again we have done the other example, trans 1,3-dichlorocyclobutane example. In this example, what we have observed, we have both the planes vertical and horizontal, and the two different we observed that the two C2 axis was present in this molecule, and because of the subsidiary and principal axis presence, we retain here D group, and because the highest fold of symmetry was 2, so we have written D2, and horizontal plane of symmetry was there. So because the plane of symmetry was perpendicular to the principal axis, we have written H. So it comes under D2H point group, and because of the plane of symmetry, the molecule was become symmetric, chiral, and shows the optical inactivity. That means the optically inactive molecule. So we have done the other example with cyclohexane. In this example, we have a cis 1,2 dimethyl cyclohexane, and we have observed that all the symmetry elements are absent except the plane of symmetry. Only the plane of symmetry was present. That's why it comes under CS point group, and the molecule is symmetric, achiral, and optically inactive. So next we have done the same molecule, but the only the cis trans difference is there. So this is the 1,2 dimethyl trans 1,2 dimethyl cyclohexane, and here we observe that only C2 axis of rotation was present. No other any symmetry element was present. No plane of symmetry on or in center of inversion or any other symmetry element was present. So because of this symmetry only C2 symmetry, we observe that the molecule was comes under the class of disymmetric, and because of the disymmetric and this C2 is comes under chiral point group, the molecule is become chiral, and chiral molecule are always shows the optical activity. That's why the molecule is optically active. Then we have done the IUPAC nomenclature. Here we have divided the molecule into three parts: prefix, parent, and suffix. Suffix was the highest priority functional group, parent chain was the longest linear carbon chain, and prefix was the substituent present on the carbon chain or a parent chain. So what we have done, we have found out the longest linear carbon chain, and because here 6 carbon atom was present, we have written hex, and uh, uh, double bond is present at third position, so we have written 3 in, and highest priority functional group is alcohol, so we have written 2 ol because it's present at second carbon atom. Alcohol group was present at second carbon atom, and the substituent present on this parent chain was methyl group, and that's why we have written here prefix as a methyl group. So 3 4 is a carbon position, and the group are present is dimethyl, so we have written 3 4 dimethyl hex 3 in 2 ol, and because we have such the EZ nomenclature, so because we have given numbering according to the priority, so first priority will be given to the ethyl group and second one to the methyl, and here the whole group have the first priority and the second priority will be given to the methyl group. Because 2 2 was same side, that's why we have written here Z. Sorry, Z nomenclature. And then we have find out the absolute configuration of this chiral carbon. So because hydroxy group was first priority group, and the second priority was given to the whole group, and third was given to the methyl group, and it was moving counterclockwise direction, that's why we have written here absolute configuration. So the molecule name was become SZ34 dimethyl hex 3 in 2-ol. Now in last example, what we have done, we have observed here, we have the longest linear carbon chain was 5 carbon, so that's why we have written pent, and the double bond was present at third position, so we have written 3 in, and second position have highest priority functional group, that is suffix, so we have written pent 3 in 2-ol. Now for prefix, we have observed that we have chlorine and ethyl group present on the longest linear chain, that's why we have written the position of carbon atom 2, and chloro group was present, so 2 chloro 3 ethyl, because at third position ethyl group was present. So 2 chloro 3 ethyl pent 3 in 2-ol was the name of the molecule, and then we find out the now EZ nomenclature of the molecule. So according to the EZ rule, we have given the priority to the substituent present on the double bond. So the first priority was given to the methyl group, and second to the hydrogen atom. And the other side, the first priority was given to the whole group, and the second to the ethyl group. So because 1 and 2 number are on same side, no, that's why it's become E group. E group, because the highest priority group are trans to each other. That's why it's become E nomenclature, E alkene. Then we have to find out the chiral carbon present in the molecule, asymmetric carbon atom. So only one asymmetric carbon atom was present. Because of this asymmetric carbon atom, we have given absolute configuration to the molecule, and the highest priority was given to the hydroxy group present on this carbon atom, then the second priority was given to the chlorine atom, and the third priority was given to the whole group. And when we were moving according to RS nomenclature, we observed that it's moving clockwise direction, that is R. But because the highest priority lowest priority functional group was present on front side, that's why the absolute configuration was inverted, and it's become S configuration. So the name of the molecule is become Se2-chloro-3-ethyl 3 in 2-ol. So I hope all of you are clear in today's lecture. If any doubt, any question regarding today's lecture is there, you can ask me in next lecture. Thank you for your kind attention.